So let me take an example in front of you. This example you can prepare in any language, JavaScript, C, C++, whatever you feel like, right? Let's take a look at this example and see how many instructions are getting executed, okay? So in line number 1, we are executing one instruction to initialize X, approximately one instruction, okay? In line number 2, there is one more instruction. In line number 3, there is one more instruction. So see, you initialize 3 variables, so 3 instructions here. In line number 4, let I is equals to X. Can I say inside a for loop, this statement is only executed once? You don't reinitialize the for loop variable again and again. This statement is executed only once. So I'll do a +1 for this. And then in every loop, what will happen? First, in one instruction, you will check the condition. In every loop iteration, first instruction will be to check the condition, then line number 5, then line number 6, and then I++. Then repeat. Condition, line 5, line 6, I++. Repeat. Condition, line 5, line 6, I++. So in every iteration of the loop, you do 4 instructions. In every iteration of the loop, you do 4 instructions. Let's say, how many iterations will be there? Let's say, let y minus x be n. Okay. Let's say the number of times the for loop is going to execute is n. So in every execution, there are 4 instructions. So can I say this is 4n plus line number 9, which is just a console.log. Let's say 1. What is the equation here? What is the, like, these are approximate. Like, I'm just trying to give you an example. We don't have to do this much analysis because after some time you will just get used to it. But overall, it looks like 4n plus 5. Overall, it looks like this. Now just think about it. If n becomes of the order 10 raised to the power 7 or 10 raised to the power 6 or 10 raised to the power 5, then 4 into 10 raised to the power 7 plus 5. Can I say this is negligible? So is this. Right. So overall, you can say that 4 and 5 are negligible. So can I say approx the number of instructions that we are going to execute is going to be equal to n. And what is n? Y minus x. So I have technically mapped your I would say number of instruction with the input size. So you can say y is equals to n. This becomes a straight line, right? This becomes a straight line, which is a technically linear curve. Right. So that's what my point is. That if you just say that this is going to take 1 unit of instruction, you can define yourself. 1 unit instruction, then initializing a variable is kind of like a 1 unit instruction, right? But the heavy instruction is looping something like this. Printing also is just 1 instructions. So when we will analyze algorithms, we are going to avoid any constant terms because it's going to take constant time. Initializing x and initializing y is not going to change if the value of x and y will become very huge. You are not going to reinitialize it like 10 times. No. You're just going to initialize it once, doesn't matter what the values they possess. Right. But based on their values, the for loop changes. Let's say now, instead of 3000, I make it 30. Then this for loop will execute only 10 times. If I make it 300, this for loop will execute approximately 280 times. So based on this input, the for loop changes. That means for loop is kind of like dependent. That's why we generalize that if there are n instructions or n iterations of the for loop, every for loop does 4 instructions every iteration. So that's why 4n, right? So that's what we have to do. And now we realize 4n is there and there is no other terms of n, and 4 can be also avoided. So the answer is going to be n. That is the overall analysis about the rate of growth of the corresponding algorithm. But that's not all about it. Technically, an algorithm can sometimes perform things based on cases. Like for sometimes the cases are so trivial that the algorithm might not even need to take a recursion or an iteration. But sometimes it is so bad that it always has to go with the longest number of instructions possible, right? So for segregating this kind of an issue, that the same algorithm, because just think about it. If I put a check here, if I put a check here, if I becomes equal to 25, break. Now, this for loop is just going to execute then 5 times, right? So best case is going to be something like this, right? So based on input, maybe let's say that some user gave the input, and let's say the value of I becomes equal to that input. So let's say there is some user input n, or let's say user input x, and let's say that user input value is 250. So from x to 250, it is going to run and then stop. So now it is dependent on the input, right? It's dependent on the input. So, but this case can change. Let's say x becomes 1, then you don't have to do a loop. Then you will, the value of n, technically number of iterations will be equal to 1, or maybe it's 0 based on something, but very less. So my point being is, for every algorithm there can be cases that for few input it can work very fast, for few big inputs only, for few inputs it work very fast, for few it doesn't work that fast. So that is why in the asymptotic analysis we have the segregation about the best case, average case, and the worst case complexity. That is, if your algorithm is going to perform very good, then how good it can be. If your algorithm is going to perform very bad, then how bad it can be. Something like this we are going to start the discussion on. So now we are going to talk about time complexity asymptotic notations, right? What is asymptotic notations? Now every algorithm can have cases, right? For example, let's say I give you an array. Let's say I give you an array, right? Inside that array, I expect you to search some element x. So what will you do? You will one by one go to the every index of x and check if the element is there. But what if the element is found on the 0th index only? Then technically you don't need to run a loop, right? You'll just go on the 0th index and get the element. You don't need to go to all of the n indexes. Whereas there can be a case that x is not even present in the array, then you will go to every index and still you will not find x, and at last you will realize you have read all of the indexes. That means it was a very bad case with respect to the first case. That's why for even algorithms like this and the more algorithms, there are different cases that can occur. For example, based on some input, some worst case can occur. Based on some input, some best case can occur. Based on some input, some on an average, like somewhere in between best case and worst case can occur. So for every different type of cases, we have actually some notations. For every different type of cases, we have some notations. So the best case notation is omega, and you also call it as big omega, right? Average case is represented by big theta, and worst case is this O, that is big O, big O, right? So whenever you have to represent the rate of growth in terms of the highest degree polynomial of the best case, then you use omega. Of the average case, you use theta, and for the worst case, you use big O. So let me write it. For representing the rate of growth in terms of highest degree terms, right? For representing the rate of growth in terms of the highest degree terms, we use these notations. We use these notations. For example, let's say if I write a loop, if I write a loop like this, for I equals to 0, I less than n, I plus plus, and there are some instructions, right? There are some instructions. So if you see, initializing a variable is a constant, then let's say there are x number of instructions per loop, but this loop is going to go n times, right? So in the worst case, the complexity is going to be O of n. A lot of people say it is the order of n, or you can say O of n, because it doesn't matter. There is no best case or something. There is no best case or something. It's just that based on the value of n, you can say that this for loop can go as bad as O of n. So the worst case actually denotes, how bad your algorithm can perform. Average case denote, that on an average, like for different variety of input, how your algorithm performed. And best case represent that for some specific best case, you will be having a bare minimum complexity that at least will be matched by your algorithm, right? That your, if your algorithm wants to perform good, how good it can be. These are complexity notations. That means, let me repeat, for representing best case of a code, you use big omega. For representing average case, you use big theta. And for worst case, you use big O. Now we are going to see the meaning of these notations very carefully, and we will see them in action also. Now, generally, whenever we talk about complexity of a function, we generally care about the worst case only, because just think about it, no? That you have written an algorithm. You don't want to always just be happy with the fact that, oh, my algorithm works very good in this best case. Otherwise, it's not that good. That's not how programmers should think, right? We should think in terms of what worst possible thing can happen. That is why this big O notation is very important. You will find a lot of lead code problems, code forces problem, which directly write big O notations in their problem statements also. Because this is the most relevant. As I said, I don't know what best case you are at or what average case you are at. So that's still handleable. That must be handleable, because worst case is going to be the worst possible thing that can happen. Also, one more thing, there can be a case that all three complexities are same. That is, there is nothing like best, average, or worst. Everything is same, or maybe any two of them are same. That can also occur, right? So first of all, let's talk about big O notation. Let's talk about big O notation. So now let's talk about big O notation. So actually, let me write about it. This notation gives tight upper bound, tight upper bound of the given function, right? Let's say, for example, if you have something like y is equals to n raised to the power 4 plus 100n square plus 11n plus 6. Let's say you have an equation like this. Let's say this fn curve is this. So let's not write in terms of y. Let's say this f of n is equals to this curve. And I am just writing randomly. Let's say this curve. Now, what big O notation will exactly mention is, it will exactly mention that if you want to find the big O of the function f of n, if you want to find the big O of the function f of n, then big O of the function f of n means that there is some function, g of n such that for all n greater than n naught, that is beyond a particular threshold, f of n will always be less than or equal to c into g of n, where c is a constant, right? Now this is a lot of maths, right? Let me simplify it for you. So what big O notation gives you? Big O notation gives you tight upper bound. Now what did I tell you? Big O is for worst case complexity. Worst case means if the algorithm is going to go bad, how bad it can go. If, like it can go as bad as what? The algorithm can go as bad as what thing? That's what big O notation is, right? So let's say that you have this algorithm, right? Now this function f of n, and or maybe let me take some simpler function. Okay, let me take some simpler function. So let's say you have something like 2n square plus 3. Now just think about it. When the value of n, when the value of n is 1, when the value of n is 1, can I say f of 1 is what? F of 1 is 5, still good. F of 2 is what? When is n is 2, f of 2 is what? 2 into 2, 4, 4 into 2, 8, 8 plus 3, 11, and so on, right? So can I find an algorithm, or let's say can I find an equation such that for a particular value n naught, if I see everything greater than n naught, then that curve is always bigger than f of n. Now you might think that, okay, which curve is bigger than 2n square plus 3? You can say n raised power 4 is bigger than 2n square plus 3. N cube is also bigger. Let's say 5n square is also bigger. All of these curves are bigger than 2n square plus 3, right? If let's say this function f of n, this function f of n is this, right? What I'm saying, I want to find a function which is having bound bigger than f of n. So if this function is 2n square plus 3, if I write a function g of n as x raised to, sorry, n raised to the power 6, then definitely g of n is greater than f of n. But that's not what we want. We want upper bound, but it should be a tight upper bound. Tight upper bound means as close as possible, right? That our function is going to perform as bad as this, never beyond this, right? So let's say we can say that this function, for example, let's say can perform as bad as 5n square, or at least better than 5n square, right? Let's say c is equals to 5. I'm not sure if c should be equal to 5 or not, but what I can say is let's just think about it. If let's say you have 2n square plus 3, okay, for n is equals to 1, n is equals to 10, n is equals to 100. Let's write some values. For n is equals to 1, this is 5. For n is equals to 1, this is 203. For n is equals to 100 is uh, this. Okay, cool. Now, if I write something like 3n square, if I write a function 3n square, then what will be the value for n is equals to 1? N is equals to 1 will be 3, right? N is equals to 10 will be what? 300. And n is equals to 1000 will be what? 30,000, right? So can I say, if I put the value of c is equals to 3, if I put the value of c is equals to 3, then we know that f of n can never perform beyond 3n square. 3n square can be set as the tightest upper limit. There can be even better, maybe 2.5n square can be even better, but generally we consider c as an integer constant, right? So what I'm trying to say is, if let's say you have a function, what big O will tell you is that your function can perform as bad as what? And this constraint should be very tight, because your function is not going to perform as bad as n raised per 6, right? But what's the closest function that I can find that will be bigger than f of n for most of the values? Something cg of n, something cg of n. So let's say I found a constant, let's say 3, that 3n square can be a function, 3n square can be a function such that f of n is less than equal to 3n square and greater than equal to 0. So I will say that 3n square is the upper bound for this function, or the tight upper bound for this function. And if I have to write that in terms of big O notation, I'll just consider this function 3n square. Now it is having this constant. I will avoid constant. So for this particular function, the tight upper bound is going to be order of n square. The tight upper bound is going to be order of n square, right? That this function is going to perform as bad as some c n square, where c can be equal to 3, but c is a constant, so we just avoid it. So if you have to measure this curve, or if you have to compare this curve with any other algorithm's curve, you don't need to compare 2n square plus 3. You can just compare n square, because it is going to perform as bad as n square only. That's what big O notation is. So let me summarize. Again. What big no, like every different case has a notation. We talk about worst case because that's the most important. What big O is that this notation will tell you the tight upper bound of a given function. And what functions are we talking about? Rate of growth functions. We're talking about rate of growth functions. So if let's say the function is something like this, its big O notation is going to be order of n square. Because what big O notation tells us is, it tells us about some function g of n such that f of n is always less than or equal to c g of n, where c is a constant, and this is valid for everything for some value n naught greater than n. Now this n naught can be even 0 or 1 or 1.5, anything. For some particular threshold, after that threshold, f of n can go equal to cg of n but cannot go beyond cg of n. Right? It can go equal to cg of n, but it cannot perform worse than g of n. That's what big O is. That my function f of n is not going to perform worse than g of n. The worst it can go is cg of n. Nothing more than that. That's what big O notation is. So at any point of time, let's say now I use this function. Let's say I now use this function. Let's say I use this function. Okay. The equation was 4n plus 5. I will say that the complexity in the worst case of this particular piece of code is order of n. Why order of n? Because this is the function of the runtime based on the input. You can see that this function can perform as bad as some cn. It can perform as bad as some c of n. Just think about it. You have 4n plus 5. Let's say I take something like 5n. Okay. For n is equals to 1, this value is what? 9. This value is 5. But for n is equals to, let's say, 2, this value becomes what? 8 plus 5 is 13. 5 into 2 is 10. Okay. For n is equals to 3, 4n plus 5 will become what? 4 into 3, 12. 12 plus 5 is 17. 5n will become 15. For n is equals to 4, this will become 16 plus 5, 21. And 5n will become 20. Now for n is equals to 5, this will be 5 into 4, 20 plus 25. Plus 5 is 25, and 5 into 5 is 25. And for n is equals to 6, this will be 29, this will be 30. So can I say, for all n greater than or equal to 6, my function f of n, let's say this is f of n, is less than or equal to cg of n, such that c is equals to 5 and g of n is equals to n. So can I say 4n plus 5 is going to be less than or equal to 5n for all n greater than or equal to 6. So my function, this function, based on the input n, can perform as bad as something like, with a rate of growth of n. It can perform as bad as a piece of code which is having a rate of growth of n. That's what I want to say. In big O notation, I try to find a function which is quite close, and my function f of n cannot go beyond this function, right? And my function will perform as bad as this, nothing worse than this. It will never go worse than this. It will be as bad as this, right? So if you are comparing two algorithms, so you can just compare based on their big O notation. That's for the worst case. So whenever we are doing worst case analysis, big O notation will make sense. We will doing some more problem solving around big O notation to actually understand how exactly worst case analysis is done. But this is all about the big O notation. So one important piece of note that I would like to tell you is, when you find a function g of n, which is technically your big O function, then that means that your piece of code is comparable to a piece of code which is having a rate of growth of g of n. So we can compare this function as this function with some function which is having a rate of growth equal to n, y is equals to n. This kind of a rate of growth is comparable here. So let's say if I have to compare this algorithm 1 with another algorithm 2, right? I'll just say that this algorithm 1 that is written here, it is performing similar to a algorithm which has a rate of growth as y is equals to n. And let's say algorithm 2 is having a rate of growth of n square. So we'll say algorithm 1 is better because this is y is equals to n, y is equals to n is better. We have seen y is equals to n is better than n square. So what I'm saying is that big O notation tells you a function which is the most comparable to you or most closest to you or the tightest to you, but in terms of upper bound, that it will be as close as you but still bigger than you. That's what big O notation is. So if I ask you a question that f of n is equals to 3n plus 8 and you want to find the tightest upper bound, what can you say? We can have a function g of n which is equals to n, and we can have a value c which is equals to, let's say, 4, and we can have n naught is equals to 8. Then we can say that f of n will be greater than equal to 0, less than or equal to cg of n for all n greater than n naught, right? You see, 3n plus 8, 4n. Okay, this is n is equals to 1. For n is equals to 1, this is what? 8 plus 3, 11. This is 4. For n is equals to 2, this is 6 plus 8, 14. This is 8. For n is equals to 3, this is 3 into 3, 9. 9 plus 9, 18, minus 1, 17. And this is 12. For n is equals to 4, this is 12 plus 8, 20. This is 16. But for n is equals to 5, for n is equals to 5, this is 23. And this is 20, right? Let me write it here. Okay. N is equals to 6. 18 plus 8 is 26. This is 24. N is equals to 7 is 29. This is 28. N is equals to 8. This is 32. And this is 32. And now anything greater than 8, can I say for anything greater than 8, 4n is always going to be greater than equal to 3n plus 8. So I can say that if exactly my function comes up with 3n plus 8 instructions, if my function, whatever code I'm going to write, if my function comes up with something like 3n plus 8 instruction, I can say that it is almost equivalent to saying 4n for every value of n greater than equal to 8, sorry, greater than 8. So this is going to be order of n. This is going to be order of n. That's what I want to say, right? Because now we are comparable to any function which is having a linear growth. N means what? Linear. N square means quadratic. So we are comparable to any function which is having a linear growth. But what function? What tightest function? Because 5n also has a linear growth. 10n also has a linear growth. But 4n is the tightest or the closest to 3n plus 8, but still greater than 3n plus 8 for n greater than 8. That's how you calculate tight upper bounds. That's how you calculate tight upper bounds, right? So if let's say I give you one more example, then let's say you have something like 2n cube minus 2n square. Let's say f of n is this. Then you can say if I write the g of n as n cube and c as 2, then f of n will be always less than or equal to cg of n for n greater than 1. Can I say that? See, n is equals to 1, 2n cube minus 2n square and n cube. This is 2 minus 2, 0. This is 1. So you can say even n greater than equal to 1. N cube is greater than 2n cube minus 2n square. If you say n is equals to 2, this is 2 into 2 into 2, that is 8 into 2, 16. 16 minus 8 is 8. Whereas n cube is what? 2 into 2 into 2, that is 8. And now everything beyond this is going to be greater, right? So that's what we can say, that if somehow my function gives me, or my code gives me, this function as the rate of growth of, I would say, instructions with respect to change in input, I can just directly compare it with something like n cube. So my complexity will become order of n cube. That's what the crux is. That's what the crux is. That if my piece of code gives me the function of instructions with respect to the, or running time with respect to the change in input as 3n plus 8, I can just directly compare it with something like order of n, or a linear growing function, because it's linear growing. After some time it's going to be something like 4n. 4n is what? N only. So we are comparing it with a linearly growing function. Now let me show you an example, and then we will try to figure out that what is the complexity in terms of big O for that. Now let's say we have a function f of 0. You see, this is a constant term. This will take constant time. Then you have a for loop that works for n iterations. There is a for loop that goes for n iteration. In that for loop, there is another for loop that goes for n iterations. So just think about it. You have a for loop, I equals to 0, I less than n, I plus plus. And then for j equals to 0, j less than n, j plus plus. Now just think about it. For every value of I, when I is 0, the inner loop of j goes n times. Then when I is equals to 1, the inner loop of j goes n times, approximately n. So like, of course, there will be 1, 2, and 3 instructions of n, but 3n is approximately n only. For I is equals to 2, again the loop of j will go n iterations, and so on. When I will become n minus 1, j will still go for n. What is the total number of iterations? Total number of iterations is what? N square. So can I say that this overall whole function f0, it is somewhere around n square iterations here, and plus 2 more iterations. That is just a return statement and a variable initializer. So some cn square plus 2 we have. Now what is the tightest upper bound for cn square plus 2? It's order of n square. So I can say the time complexity in the worst case is order of n square. In the worst case is order of n square. And what does n square signify here? What does n square signify here? That with respect to change in your input n, your overall function's rate of growth is going to increase with the rate of n square. Right? Just think about it. If n is 1, this for loop will run for what? 1 iteration. Okay. If n is 10, this for loop will approximately run for 100 iterations. If n is 100, this for loop will run approximately 10 raised per 4 iterations. If n is 10 raised per 5, this for loop is going to run approximately to 10 raised per 10 iterations. Right? So the rate of growth of this function is equivalent to a n square curve. That is a quadratic curve. So we say that my worst case complexity is as bad as order of n square. That is, my rate of growth is as bad as a n square curve. That is the meaning of time complexity analysis in terms of the worst case. So I would like to give a tip for everyone. Like when we will be doing algorithmic questions, when we will be actually doing coding, then you don't need to write all of this inequalities and everything. All you have to do is just take a look at the code. Whatever code is in front of you, just take a look at the code. Try to find the most approximate function that can help you to understand the complexity or the rate of growth of that code. You don't need to always do this much amount of inequalities, then figure out for what value of n you have to do. This we are doing because technically this whole topic is coming from a bit of mathematical background. That if let's say someone theoretically asks you that for f of n, tell me the constant for which g of n will become the big O notation for f of n, then you need to find this constant like this, right? But in actual day-to-day coding, you don't need to do all of this inequality. All you have to do is what we did in function f0. That is, we approximated that for how much iterations the loop is going. We approximated that the overall code is having a rate of growth similar to a n square curve, and hence the complexity is order of n square. That's what you have to do as a day-to-day coding exercise.